All right, this is unit 4.2, doing more with least squares regression, scatterplots. Um, Again, this is going to have a lot of interpreting, and some of this we actually already have seen in 4.1. I kind of introduced it a little bit, so some of this might sound familiar or be a little familiar, at least in terms of what you may have just seen, but obviously we'll go into more detail here. So let's get started. So the regression line, as we talked about in 4.1, describes how a response variable changes based on how the explanatory or x variable changes. Basically, you're connecting the two quantitative variables together. It's kind of a prediction of how it's going to change based on a previous set of data, right? You take a set of data, and then you look at that set of data, and you try to make kind of a overall prediction of where you expect data to fall if it were to continue on that pattern or be contained within that pattern. Okay. We again often use it to predict the y value given a specific x value. Okay. A regression line, as we saw in the previous section, takes the form of kind of a line, right? Y equals mx plus b. Sometimes you'll see it like this. That's not the highlighter. Sometimes you'll see it like this. Y hat equals a plus bx. And the other times you'll see it as y hat equals mx plus b. They mean the same thing. The only thing, just make sure you understand that in this case, the b is the slope, and in this case, the m is the slope. So it doesn't really matter as long as you just remember algebraic understanding of what slope is and how it's written in a linear equation. Okay. Y hat, again, we talked about previously. Y hat is the predicted value for y. It's important to understand that this is always talking about predicted values. It's not necessarily what it exactly is or will be, but it's what is predicted. And obviously we have a slope, which is interpreted as the amount of change in y for one unit change in x. And then the y-intercept is the predicted value of y when x is 0, which doesn't always make sense logically with the context, but it is something that we can figure out. Okay, so here's what we have. This is quite honestly something you should already be able to do. If you want to pause and try this problem, you can. But let's take a look. So we have a table and a scatter plot describing the relationship between the miles driven, explanatory variable, and the price of used Ford F-150 Super Crew trucks. So it would make sense that the amount of miles driven on a used truck might influence the eventual price that it was sold at, or a used dealership, or whatever the case may be. Also makes sense that miles driven is not the only variable that affects this, so it won't be a perfect, for every mile driven it goes down by 10 cents. That's not how it's going to work. But in general, trucks with 120,000 miles will usually cost less than trucks that are 60,000 miles, right? So you can see the data there. You can see a table. You can see the scatter plot drawn. It already has the kind of the regression line drawn in there. And then something you should know by now from watching the video is how to get this equation. You don't have to do this right now, but you should be able to get that using your calculator. And you have y hat equals 38,257 minus 0.1629x. And then you're also told the correlation coefficient R, remember that's correlation coefficient is R, is negative 0.815. Remember, negative makes sense because of the slope being negative, negative association, all those things. And pretty strong. 0.81 is fairly close to 1. Again, it's not perfectly linear, but it is a fairly strong association there in the negative direction. So describe in context which each of these mean. Remember to use values or words like predicted and expected. Again, you might have already tried this on your own. If not, the 38,257, it's not multiplied to x, it's a y-intercept. Remember, a y-intercept is always 0 for x. What's the predicted y? So in this case, if a truck had 0 miles driven, it would have an expected price of 38,257, which actually kind of does make sense. It's kind of like the new version of that truck. Does have some meaning, at least. Might not be perfectly accurate, but it does have some meaning to this. Negative 0.1629 is the slope, which is always talking about change in y for one unit change in x. So the expected price of a truck goes down by about 16.3 cents, right? 16 cents for each additional mile driven. Okay, so again, that value changes for every one additional unit in x. And then correlation coefficient always talks about direction and strength for the linear association here. So the relationship between miles driven and price, again, you want to say those words. You don't just want to say strong, negative, linear. Okay? Is it moderately strong, negative, linear association? Moderately strong, I think, is best here. It's not necessarily perfectly strong or strong. There is no value that changes from moderately strong to strong. I think it's, again, just a feel thing. Generally, in the 0.7s and 0.8s, you're probably moderately strong. Once you get lower than 0.7, you're probably getting to strong or more like moderately weak, or, there's some flexibility there, okay? Again, negative, linear, association, all those words kind of need to be there. Some sort of talking about strength and some sort of direction, and then obviously you're talking specifically about the linear association. Okay, that should be stuff you already know. This one also probably could be stuff you already know. Using the graph to predict the price for a truck that has 100,000 miles. So you can see kind of from this line here, you just basically go up from 100,000, you go over approximately 21,000. That's not a perfect estimate because quite honestly, you might be kind of guessing there at the 21,000. So the better way to do this, more accurate representation, is to use your regression equation, okay? 100,000 miles is an x value. All you have to do is plug in 100,000 for x, and you get that it's about 21,967. So maybe that line needs to be a little higher. I don't know. It's not that big of a deal. Obviously, the important thing there is you can use the graph to get an idea. If I didn't give you the equation, or you didn't have the equation, you could get a general estimate. If you do have the equation, you're still getting an estimate, because remember, it's still a prediction, okay? But it's probably a more reasonable prediction given you use the equation. And then finally, use the equation to predict the price for a truck that has 250,000 miles driven. Why might this be an issue? What might be the issue with doing this? Again, you could plug 250 in, 250,000. You get negative 2,468, which should like pop up as a light bulb for you. Like, are they gonna pay me $2,500 almost to take the truck away? No, probably not. The bigger issue here is if you look at 250,000 miles, that does not fit within the data window here. Okay, we're only going up to 100,000 miles. Now, it's possible in certain contexts that if you go past, that the pattern will continue, except we don't have any data showing that. And it's likely for us to think that even as the miles go up, the price will start to kind of curve off, right? Kind of like not quite continue the linear pattern. Again, and this is something that is called extrapolation. Basically, we are not allowed to make these big predictions outside of the window of our x value, okay? Or really, quite honestly, the y value too, especially if it doesn't fall within the x. So extrapolation is when we're using regression data for a prediction that's really far outside of what the previous data shows. Remember, we're using the previous data to get our regression equation. If we're outside of that window in terms of especially the x direction, we don't necessarily know for sure if that pattern continues, okay? So be careful with that. That doesn't necessarily give us accurate data and likely will be an incorrect statement to make, okay? Feel free to try this next one if you'd like. And if you wouldn't like, then we'll just go over it right now, okay? A scatter plot is shown below that examines the relationship between height and arm span, both in inches, of certain individuals. So the height is the explanatory, and then the arm span is the response. Probably makes sense. You kind of look at the person's height. Wow, that person's tall. Oh, and look, because of that, they have a pretty wide arm span. If you looked at someone's arm span and it was pretty long, you probably could rationalize that they're probably pretty tall, but usually you'd probably look at their height first. That's why that's the explanatory. I do give you the regression equation here. Again, y hat, don't forget, predicted arm span based on height. Explain the significance of the y-intercept and slope. Y-intercept is that 12.5 value. Remember, that is if the x is 0. In this case, if a person is 0 inches tall. Yeah, try to think about that. It would be predicted they have an arm span of 12.5 inches. That would be remarkable. let me just say, if you were that person, that would be impressive, okay? Obviously, that doesn't logically make sense, but that is technically what the data suggests. Now, that basically is another reason to understand extrapolation. This data is only to as low as 58 inches. Obviously, if you start going down lower and lower and lower, one, there's no such thing as a person that's 0 inches tall. But basically, this pattern will not continue in this linear way all the way down to 0, right? So that's an understanding of why extrapolation is important to understand. Slope, for each additional inch of height, a person's arm span is expected to increase by 0.811 inches. Again, you could say that either direction. You could say the arm span is expected to increase by 0.811 for every additional inch of height second. You could say that second. Doesn't matter the order, but it always has to be 1 unit up in the x direction and then the slope change in the y direction. Again, increase because it's positive slope. Predict the arm span of a person in this model is 5 feet tall. Keep in mind units are inches here, so you got to convert to inches. That is 60 inches tall. And if they're giving you 5 feet tall, 60 inches tall, that's an x value, that's a height. You plug it in the equation there, you can see there it's approximately 61.16. And I say approximately because, again, one, you're predicting, and then also with rounding issues and stuff. Generally, you want to go to 2 decimals. They sometimes will give you more, but if you, as long as you show your work, you go to 2 decimals, you'll be fine. And then the other issue, the other part, letter C, they actually give you an arm span this time. So you're kind of working backwards to figure out that that person possibly is about 75.83 inches tall. This time you plugged in for Y. Okay, and again, you could use the chart, the graph, you could kind of go up and over and whatnot from the numbers, but since you have the equation, it's much more reasonable and probably the best way to do it. What would be the arm span of someone who's 7 feet 5 inches tall? Holy basketball player. All right. Should we trust the accuracy of this prediction on the model? My guess is me just saying that question means you probably think no. But the reason it's a no, you could plug in there, and remember, you have to convert to inches, 89 inches. The reason is, again, hitting on the extrapolation piece, this only goes up to 78 inches. It's reasonable to think that as you get much taller, somehow arm span changes a little bit. It also is possibly reasonably to think that maybe it doesn't change, the pattern continues, but we don't know that, right? We don't know. So we don't have data showing really tall people in this case, at least that tall. 6'8", still pretty tall. 6'6", whatever they got. But 7'5", we don't have data up to that tall, that height, so we can't extrapolate to that number. So we don't trust that very much, even though it's quite possible that it does not change. All right, so that really is nothing new there. That's probably more or less stuff we've already done. Now we're going to get into stuff that's new. Okay, so here we go. Something called a residual. A residual is the difference between an observed value of the response variable and the value predicted by the regression line. Okay, that's statistically speaking. Here's what a residual really is, okay? Let's look at this data point right here, okay? That's somebody's, this is miles and price. This is back to the Ford 150 Super Duty, whatever truck it was, okay? This guy right here, okay? This is an actual truck, right there. We had data. This was the regression line that we calculated based on the data, okay? Here's what a residual is. I don't know the exact cost here. That's about 25-ish, somewhere in there. My line wasn't perfectly straight, but whatever that miles driven is, okay, whatever that miles driven is, here in, just to change up the colors, here in orange, kind of orange, that price, about $35,000, that is what we would predict. Based on this data, we'd predict that a truck with this many miles would have a cost of about $35,000. But this truck didn't. This truck had that number of miles, but it was upwards of like $42,000, okay? The residual is the difference in the y direction, from the point to its predicted value for that number of X units, okay? That's the residual. The residual is how far off it is from what was predicted, is basically what it is. Okay, so our regression data basically tells us what we should expect a truck to cost with that many miles, but this one was higher than that by about 7-ish thousand or so. So this would have approximately, again, I'm just making up that number, about a positive $7,000 residual, okay, which basically is assuming 35,000 and 42,000, okay? You can have a positive residual when the actual data value is above the predicted line. It has a higher Y value than predicted. You could also have a negative residual. If you look at that one right here, okay, that data point is below the predicted value by a few thousand. So that residual would be negative how many ever thousand, okay? So a residual is how far above or below in the Y value that a certain data point is based on what's predicted, okay? So technically, it's this equation, the observed or actual Y value minus the predicted Y value based on the regression line, which you consider it as Y minus Y hat. I ignore this. I don't even do that. I just conceptually understand the following. Here's what it is. How far above or below is it from what was predicted? If your value is higher than what was predicted, you have a positive residual. Again, doesn't necessarily mean it was good or bad, just a positive residual, higher than expected. If you're lower than expected, what would you think you have? Oh, I don't know, maybe a negative residual. So I don't really I don't think about this. Some of you guys will be like, well, what's the equation? Forget about an equation. Understand what it means. A residual is how far above or below, up and down, always up and down, Y values, how far above or below the actual data value is from the predicted one, with specifically being above the predicted value, a positive, and below the predicted, a negative. Okay? All right. You'll have plenty of opportunities to practice that. Now, when we use line of best fit, sometimes we say line of best fit, sometimes we call it a regression line. The best term is an LSRL, which you'll hear me say least squares regression line. Here's what your calculator magically does in literally hundredths or thousandths of a second when you press and then it says, okay, here's the equation of the line. Here's what the calculator does to come up with the actual quote-unquote line of best fit. The line of best fit is the best fit by the following reason, okay? Here's what it does. It takes all of the data and it calculates residuals. Residuals are, again, how far above or below. And if you tried to average out, like you want residuals to be minimal, right? Because what does a line of best fit do? What does a line of best fit do? / what does it do? Is it's best representing all the points collectively. So it should kind of like go through the middle of the data. Okay, this is not a line of best fit for that data because it's way off on pretty much everything. Okay. So we want to minimize the residuals. Minimize the residuals means make those dots as close to the line vertically as possible. Keeping in mind it has to be a straight line. But if you think about this, if you just said, well, let's average out the residuals, right? Because the smallest average. But what is a positive and a negative residual going to start to do? If you add a positive and a negative value, they're always going to kind of go close to zero. So they're always going to balance each other out. So just averaging residuals doesn't work. So what you need to do, you don't need to do, you need to understand, is what they do is, I know this is a weird picture, but they square the residual, okay? And I know this is a square. Yes, technically. They square, like raise it to the second power. So if a certain residual is -3, they square it, which really makes 9. If a residual is +4, they square it and they make 16. Okay? And then they add up all of those squared residuals. Notice they'd all be positive because it doesn't matter if you're positive or negative. When you square it, it's still going to be positive. But if the root of the problem, if the original residual is a bigger value, either positive or negative, doesn't matter. If it's further from 0, when you square it, it's going to be a bigger number. So we want all of these squared residuals to be as small as possible. But technically, it's got to be all of them. So what they do is it's the sum of the squared residuals. The least squares regression line takes the sum of the squared residuals and makes it as small as possible. Because if the sum of the squared residuals is as small as possible, that means that line reduces or makes the residuals as close to the line as possible, which makes it the best fitting line deemable, right? So what your calculator literally does in a moment's notice is it takes all these algorithms and basically spits out in literally less than a second the single best equation of a line that makes the fit the best based on minimizing the squared residuals. So what you need to understand here is when we say least squares, that means is we are making the sum of the squared residuals, aka squares, as small as possible, which is least. Okay? Will you have to do it by hand? God, no. Will you have to plug it into your calculator? Yeah, you've already done that. Do you have to understand kind of what's going on here? You do. Should you maybe already kind of get that a line of best fit literally should be the best fitting line? Yeah, but now you get what that means. If you've ever heard line of best fit, now you know what it means. It's the best fit because it minimizes those vertical distances from the line, but specifically the squared vertical distances, and get them all added up. Okay? Now, could there be a question saying something like, what does least squares and least squares regression line mean? Yes. What does that mean? It means we're minimizing the sum of the squared residuals. If you miss the word sum, wrong. If you miss minimizing, wrong. If you miss squared, wrong. If you miss residuals, wrong. All those words need to be there. It's making the sum of the squared residuals as small as possible or minimizing that. Do you have to do it by hand? No. Do you need to understand how it's happening? Yes. Understanding how it's happening gives you a better understanding of what the hell a line of best fit or least squares regression line actually is. Okay? Cool. All right. We have the data again. That was our F-150 scatter plot from before. Sometimes I like to stay with the same data just to keep consistent. Okay, there's the equation. Find and interpret the residual for the Ford F-150 truck that had 70,000 miles, 70,583 miles, and cost $21,994. That is a certain truck. That's this one. Now, keep in mind what a residual is. A residual is how far above or below the predicted value for Y that truck had. So what we do is we need to know what was the predicted value. We know the actual value for that truck, $21,994. I want to know what was predicted based on the equation for that truck. So I take it and I plug it in for X. I plug my X value in for X. And I get 26,759. What that number is how much we would have expected this truck with 70,583 miles to cost, or its price, based on our regression data. However, it didn't actually cost that much. Okay? So you find the difference between how much it actually cost and how much it was predicted to be cost. And that difference is $4,765. Now, the confusion is, I think everybody will be fine with understanding, okay, you subtract those numbers. Is it positive or negative? And the simple thing is, was the actual truck price higher or lower than what was predicted? This is the actual truck price. This is what was predicted. It's lower, it's a negative residual. It costs less than you would have expected. So what does that mean? The truck's price is $4,765 less than what's predicted for similar trucks with this amount of mileage. Okay? Again, based on this regression data. How we feeling? Cool? Ready to try another one? Good. Good thing you can pause it and refresh, and I don't have to wait 10 minutes. Okay? Find and interpret, similar thing, but now we're doing it for 140,000 mile guy. That's this one right here. Okay, same thing. I know that its cost is about $21,000, but I want to know what it would have been based on the predicted data, right? The prediction from the regression line. So I plug in my X value of miles, and I get that it should have been or it was expected to be, not should have been, but expected to be based on this data, about $15,324. This one was more. I don't know. Maybe it was in really condition. Maybe it had certain other, features on it. Whatever. Who knows? There's lots of things you could come up with. But it's higher than what was expected. So you subtract, and then since it was higher this time, you expect it to be a positive residual. Okay, this price was actually higher than what we would have expected. Okay, and that's again what the interpretation is. It's higher by that much money than what was predicted for. Again, this is important for similar trucks with this amount of mileage, right? For like, that's kind of, it's not for any truck. It's not for any car. It's just for these types of trucks with that amount of mileage. You could have added another one right next to it with the exact same mileage. It would have went for 10,000 more. Who knows? Okay, but this is what it was predicted for that. Okay. All right, so this next one, feel free to go ahead and try it. You see some points per game for SEC football teams and the number of wins. Obviously, you would expect more points scored for your team means more wins. That doesn't always happen the case for sometimes, but here's the regression data. Here's the regression equation. See if you can do some of these things. I'll give you a minute. Okay, minute's over. Hey, way to go. Okay, label the scatter plot. If the variables were switched, do you think the least squares regression equation would be the same? Okay, so points per game predicts wins. Very simply. Okay, there's really no other way to do it. You can't have a win until you get some points per game, right? The variables were switched. Do you think the least squares regression line would be the same? Well, no. It still has a positive association. So as wins goes up, you would expect points per game to go up, but the slope would be different. I mean, that part alone makes it understand why it would be different. Points per game per win versus wins per point per game are two different things that might both be positive, but they would be wildly different values. Okay, so the slope, y-intercept, those things would not be the same. Okay, you wouldn't expect to have the same number of wins at 0 points per game as you would to have points per game for 0 wins. Right? You score 0 points per game, you probably have like literally no wins. If you have no wins, you could still have some points per game. Those things are going to be different. So don't think that it's okay to just switch the variables, put them wherever you want. There is a right and wrong way. Explaining context with slope. We've done this a ton. You should be getting really good at this. Slope is the predicted number of wins, in this case, increasing by about 0.4372 wins for each additional point scored per game. Okay. And then y-intercept, if the team scored 0 points per game, they should expect to have negative 3.75 wins, which doesn't make sense. You would likely possibly have 0 points per game. I mean, that's possible. You just probably won't have any wins. You won't have negative wins, that's for sure, but that's technically what that means. Okay. All right. Find and interpret the residuals for Arkansas and Vanderbilt separately. So again, you plug in their actual X value. You plug in for Arkansas its actual number of points per game, and you get that it was predicted to have 12.34 wins, except they only had 11. Okay, so they were less than what was predicted by 1.34 games. They won 1.34 less games than what would have been predicted based on the amount of points they score. Okay, why? I don't know, they scored a lot of points, but maybe their defense sucks, so they gives up a ton of points too. So they score a lot, but they also give up a lot, and they didn't win as many because some of the games they would have likely won previously with the number of points, maybe they didn't win. Okay, I tell a lot of stories here. Okay, and then Vanderbilt, same thing. You plug in its number of points per game. Always you plug in the X to get the predicted Y. And this time the predicted Y was 7.92, and they also were less. They only had 6 wins, which means they were almost 2 full games less, 1.92 specifically, than what was predicted. Okay. Then kind of a curveball question here. This one's kind of tricky, or it makes you think a little bit. U of I, there you go, Askiwawa, scored 294 points that same year over the course of 13 total games. This data is actually real from, I don't know what year it was. What year did I say it was? Some year. I don't know. It was a year. I actually found the data for real. the Illinois scored 294 points that same year over the course of 13 total games using the SEC's regression line. So now U of I is not in the SEC, but let's say if like we followed that same pattern, they had a residual of 0.86 if you followed that same pattern. So this is different. This time I'm not telling you how many wins they got, but I do tell you their residual. So you're kind of working backwards. So first of all, 294 points per game over 13 games gives you 22.6 points per game. That's an X value, so you can plug that into here. And using that, you get 6.13 predicted wins. Except they had a positive 0.86-ish residual, meaning they actually won 0.86 more games than was predicted because they have a positive residual. So if you add the 0.86 to the 6.13, you get what essentially turns out to be, if you had ignored rounding or the rounding was a little bit more to decimals, what was actually 7 games that year. Okay, so they won 7 games, even though they were only predicted based on their points to win 6.13. Again, based on the SEC model, I just made this up. Don't like the SEC, like the Big Ten, so I wanted to get that in there, but whatever. Okay. Again, there is much more math here than there might have been in previous units in this class, but again, you still have to connect the conceptual. You still have to understand what you're doing. If you don't understand what you're doing or what it is you're finding, then you're not going to be able to do this. Okay, that's the truth. All right, this next step. In previous years, if we were doing this in class or whatever, and maybe we still are, depending on what year it is, I would skip this. I'd be like, okay, here's what it is. Let's move on. Okay, you have a formula sheet in this class. These are on the formula sheet. I'll just quickly kind of show you what it is. I probably won't ever test you this in class specifically. It's not the most important thing. I don't see it very often on tests. Before the AP exam, we'll definitely make sure you get it or understand it enough. But for right now, just kind of a glance over. If you get this, great. If not, I might not ever talk about it again until we just absolutely have to know it for an AP test, to be honest. Here's 2 equations that are on your formula sheet. Okay. Keep in mind, given this format, B technically means slope. Okay, given this format, B is slope. What the slope can always be equal to the R, which is the correlation coefficient, times the fraction of whatever SY over SX is, and those are the standard deviations of the Y/X variables. Okay? So in previous units, we have taken a single set of data and found mean and standard deviation and stuff. So if I looked up here real quick, if I looked at the points per game, the X values, I could put just that single data in a list, and I could get the standard deviation of those points. Okay, I could do the same thing for the wins. And if I did that, I would take the standard deviation of the Y values divided by the standard deviation of the X values, and I'd multiply by the R, and that would give me the slope. Like, it's just an equation that works, okay? Now you might be like, why am I ever gonna have to do that? Possibly. In a multiple choice question, when they give you an R, and they give you a standard deviation of the Y, and they give you a standard deviation of the X, you might have to do it. Are you ever gonna have to do it by hand? No. Are they gonna give you a list, and you're gonna have to calculate 2 separate standard deviations and a correlation coefficient and multiply it? No. But technically this is a thing that happens, okay? How do you likely know this is going to be a question? Because if they ever tell you something about the standard deviation of the Y and separately the X values, you pretty much just plug in the equation. That's it. Okay. The second thing that's helpful, I suppose, is this. And remember, the A is the Y-intercept. Okay. X bar and Y bar. If you remember, X bar is the mean, right? The sample mean. Okay. X bar is technically the average of all the X values, and Y bar is all the average of all the Y values. Again, kind of like what I just did with standard deviation, except mean. You could do that a little easier. You wouldn't need to necessarily use a list. This is helpful to know. The least squares regression line will always go through the coordinate that is the average X and average Y. Like whatever the average X and average Y is, the line will always go through it. So basically, if you just replace the y hat and the x with a y bar and an x bar, it'll work. Now again, how is this helpful? It's not, except they might give you the average y value, they might give you the average x value, and then either a slope or y-intercept, and ask you to compute it. I have never seen it come up. Aside from saying last minute before the AP test, hey, don't forget about this, let's try maybe one problem and make sure you get it, and plug and chug basically. There's really no reason to understand it. So I'm actually gonna not even go over this example. I don't wanna waste the time here. If you wanna try it, basically you're just plugging in numbers and kind of solving backwards. Whatever, okay? You can do that if you'd like. I'm gonna skip it. I don't think it's that big of a deal. But enough to say, not enough to do right now, okay? Because there is other stuff we need to do, like a residual plot. A residual plot is plotting the residuals. It's crazy to think about. Only. Like you're just taking the residuals and focusing on the residuals. Okay, basically it takes the original scatter plot and kind of turns it and makes it a residual plot. So you're like, what the hell are you talking about? Here's what it is, okay? This is easy to understand if you just look. Here's the original scatter plot. Again, miles driven, price, F-150. Everyone go buy one, okay? I don't care. I'm just kidding, okay? Remember, residuals are how far above or below, straight up, straight down, the actual values are from the predicted, okay? So like, let's say this one right here, I don't know what that is approximately. Let's see, that's 28. Let's say it's about 7,000, okay? For this X value, whatever that is, at about 70-ish thousand, the residual for that data point is about 7,000. So if you went to here, that same data point, which is right here, notice it is exactly, or you know, whatever exactly would be for you here, 7,000 units above technically zero. Okay? So it's just basically taking every residual, positive or negative, and plotting it against a horizontal line at zero that stays consistent with the X values. So this still references price, but it doesn't actually include the actual price. It's more the residual price value, okay? So if you looked here and you connected the dots, more or less, you could see this one, which is really close to the line, it has like barely any residual, so it's really close to the line. Whereas one that's a lot further is got its residual shown there. So really it's just, I mean, you could turn, I'm turning my iPad, but you can't see that. If you literally turned this graph and you kind of turned it to make the line of best fit, regression line, if you made that this line, basically it's the same graph. Because however high or low these points are is however high or low these points would be. Okay, so this is a residual plot. Okay, why is this helpful? Here's why it's helpful. Notice in this residual plot, the points are literally scattered. It's like you took some paint, put it on a brush, and you kind of flicked it at paper, and you'd have like scatter just all over the place. No obvious pattern, some higher, some lower, just kind of all over the place, okay? When that happens, it means that these points were randomly scattered along the line, which generally means that that line is a good model, that a linear model is a good fit for the data. Okay, it's a good fit for the data. Because there's going to be some points above, there's going to be some points below, and there's no pattern. The big thing is like random scatter with no pattern. Conversely, if you looked at this scatter plot, this is an actual scatter plot, this is not a residual plot because the line's not going across, okay? Look at the data. That's very clearly curved or almost parabolic in nature, okay? If we tried to fit a straight line through that, the question is a straight line a good model for this when we could technically use curved or some exponential graph? And you probably would say no, like that's not very good, right? But look what happens when you turn this into a residual plot. This is the residual plot for this, okay? Early on, there's some negative residuals. You get something close, and then all of these consistently stay above and then go back to negative, okay? What you notice about this residual plot is that there's not random scatter. There's a clear, it doesn't have to be that perfect. That's pretty perfect parabolic pattern. But like clearly like a non-scattered pattern. That means that the original data, a linear model, is not good. Okay? So I could show you this and say, hey, whatever line is used here, was that a good representation? Whatever equation, was that a good linear model? Was that represented well? And you'd be like, no, because there's obvious pattern and no random scatter, then that's an issue, okay? All right, so that's what a residual plot does. Are you gonna, could you make a residual plot? You could. Are you gonna have to? No. The question is gonna be this. Here's a residual plot. It might ask a certain question about a couple little things, okay? Like which of these seems to have a residual of about 3,000 or something like that, okay? But more likely what it's gonna say is a linear model good or appropriate for this data? And they're not gonna give you this, because you'd be like, hell yeah, lines all the way. Okay, you have to look at this. Random scatter, no obvious pattern. Okay, and it'll be either clearly random scatter and no obvious pattern, or obvious pattern. Okay, and definitely not random scatter. All right, here's the practice here, okay? Again, feel free to pause it if you'd like, or just keep going, whatever you gotta do, okay? As I said earlier, you most likely won't have to graph a residual plot, but rather interpret what's going on. Here we have a group of hikers in northern Michigan. Prior to leaving, they each had to be weighed and have their backpacks weighed for safety protocol reasons. That sounds like fun. The data shown below shows these weights, and a residual plot is also shown for these data. So it makes sense, possibly, that the body weight of a person, a bigger person, likely is able to or allowed to have a bigger backpack weight for, physical restraint and whatever reasons, health reasons, whereas someone that's maybe smaller likely should not have as big of a backpack. Who knows? Whatever. I don't know what they're looking for here, okay? First of all, find the least squares regression line. That's equation. You plug the data in, right? Hopefully you've known how to do that. If you did not do that on your own right now, hopefully that's something you feel good on. I did the y hat equals mx plus b version. If you switched it, it would just be switched, but 16.2x plus. X is the body weight again, and y is the backpack weight. Remember, y hats, don't forget the y hat. You forget a y hat when you're writing a least squares regression line, that's points off. Explaining context convex the slope. You should be getting really good at this by now. The expected backpack weight, the y value, increases by about 0.09 pounds. That's the y variable units, right? For each additional pound of body weight. Is a linear model appropriate for this data? See residual plot. Okay? See this residual plot. Okay? Is there random scattering? Yes. Is there any obvious pattern? No. Okay? So it appears as though a linear model is seemingly appropriate. It's not probably as great as we'd want. If you see some of these are closer and some of these get to be bigger further away, that's maybe a sign that there's something peculiar going on here. But it's definitely not some sort of curved pattern. It just might be a little more scattered and maybe just not very good correlation. Okay. A 9th hiker in this group was in the bathroom when they're getting weighed. Her data is not represented here. If she weighed 150 pounds and her backpack weighed 28 pounds, draw on the residual plot where her data value would be based on her group's regression equation. Okay, so different question here. This is definitely something that could have come up on an FR. You need to find her residual first. So she weighed 150 pounds. That is an X value. You plug that in for X, and you find that her predicted weight backpack should be 29.76 ounces. Her backpack weighed less than that. So she has a negative residual. Negative 1.76. You go to like whatever that is approximately, you kind of go over and make sure you're at her specific weight. You're done. Okay? Cool. All right. Of all the things you need to interpret, this one is the one that most likely you're like, I still don't quite get it. And it's also the one that is most likely, as long as you just kind of more, I don't want to say memorize, but I'm going to say kind of memorize the statement, the interpretation, you're going to be okay. Okay? It's called the coefficient of determination. It is technically r squared, which is actually, yes, the actual r squared. It will always be positive. And since r is always between 1 and -1, when you square a number that's between 1 and -1, this also will be between 1 and -1. Except it's squared, so it will be between 0 and 1. And it is technically the fraction or percent of the variation. Okay, it'll be heavy here for a second. Hopefully then you'll start to figure it out. The fraction or percent of the variation with respect to y that is accounted for by the least squares regression line of y on x. Holy you know what, okay? The least squares regression line relating the y value to the x value, the y variable to the x variable, the response variable to the relationship between these on the regression line accounts for whatever percent of the variation in the response variable. Okay. So here's what I think is the easiest way to understand this, okay? Here's what I think is the easiest way to understand this, all right? And I'm going to go to here. This is great, okay? I don't know what the r squared is for this, okay? I don't. I'm just going to write a number out. I'm going to say r squared. Actually, we might know it. What was the miles driven? Sorry, un minuto, por favor. Hold on. Did we have the r value for this guy? I don't know. I don't know if we did. I don't know. Okay, doesn't matter. Whatever. I'm going to make it up. Okay, whatever the r value is, it is literally that value squared. Okay, I'm going to make it up. I'm going to say 0.84. So whatever the square root of that is would be your r. Okay, let's say that the miles driven truck price scenario that we've talked about 3 or 4 times has an r squared, a coefficient of determination of 0.84. Here's what this means. That is a percent. 84%. Here's what this means. Would you agree that the y values aren't perfectly on the line, right? They're not perfectly on the line, meaning the data is not a perfect line, okay? If the data was a perfect line, if the data was all on this line, every single point was like literally on the line, basically what we'd be saying is the relationship between miles driven and price is like a perfect correlation, meaning miles driven is literally the only thing that tells you the price of the truck, because as the miles change, the price changes in the same exact sloping way. Okay? That's not the case, and likely will never be the case for pretty much any 2 quantitative variables. So here's the thing behind this r squared idea. Okay? It is the percent variation of the response variable, like the difference in the response variable when you connect these 2 variables together, all right? And again, you can go down to that interpretation and read through it again. Here's what it means. I alluded to this earlier. Is miles driven the only thing that influences the price of a car or a truck? Look at these 2 spots right here, those 2. They roughly, maybe this one be better. These 2 seem to have the exact same or pretty damn close to the exact same number of miles driven. Yet they're wildly different in terms of price. What other factors might there be for why those prices are different? Right? Some of the things that are on the truck, maybe they have the same number of miles driven, one has more damage, one's been more accidents, different color. There's any number of things, right? Probably a lot of the technology and things that are on there is a big factor, okay? So here's what this is saying. In general, when you compare price versus miles driven for these trucks, 84% of the reason why these aren't perfect has to do with this relationship, okay? 84% of the reason why the price is not there, the variation in y, the reason that the price is not perfectly predicted, 84% of that reason, or that variation, can be taken into consideration because of miles driven. So we're kind of like saying, not exactly, kind of like saying there's 16% of the reason why these points aren't on the line is because of something else. Damage to the truck, previous accidents, features on the truck. Like 84% actually is pretty good, right? 84% of the reason why those prices are like not quite there is accounted for because of the miles driven relationship. Okay? So the closer that this is to 1, the closer that these points will be on the line. Because if miles driven is the only factor, and there's no alternative, don't think confounding, but kind of, right? If there are no other variables affecting price other than miles driven, these points should be much closer to the line. So an R-squared value closer to 1 means that there is not many other factors besides miles driven. The variation is accounted for mostly by miles driven. Okay? If you had data points that were way off, you're going to have an R that's way off or smaller, and you're going to have an R-squared that's way smaller. Meaning there is small amount of variation explained because of the relationship between miles driven and price, but there's going to be many other factors that probably are weighing heavily. So hopefully that kind of makes sense, right? It's related to saying the relationship between these two variables, how well is this predicted based on its relationship with that thing. If the data is close to the line, R-squared will be higher because pretty much all of the variation is predicted by miles driven. And if it's not close to the line, R-squared will be smaller, which means there are many other factors. There's only a little bit of the variation is predicted by miles driven. Okay, we can only in a scatter plot relate to one variable, right? The y can only go to one variable. We could graph price versus, I don't know, cost of damage on the truck previously, and that would be maybe a different graph, right? So that's kind of what this is said. Now, this equation, this line right here, is basically your carbon copy thing. The least squares regression line relating y variable to x variable, obviously you put in context what those are, accounts for r-squared decimal percent, however you want to write that, of the variation in the y value. It's always talking about how much the y value varies, right? How much does the y value go away from the line? That percent of that variation is explained or accounted for by this relationship between these two variables. Okay, again, like I said, that's the hardest one to understand. You're going to have lots of time to practice it. And I'll think of new ways and other things to do to help you kind of understand it, but that's kind of where we're at right now, okay? All right, so try this using the SEC points per game and wins data, and then we'll kind of go from there, okay? All right, interpret the R-squared. I tell you the R-squared, interpret it. Again, you're just basically saying, so the regression equation relating y value to x value, points per game, and wins, accounts for 87.6% of the variation in wins. Meaning, the reason that the wins differ from what was predicted, a lot of that is accounted for because of points per game. There's other variables there, maybe defense and other things, okay, luck. But a big chunk of it, you score more points, you kind of win. It's kind of predicting pretty well, okay? What might be another factor affecting the number of wins? Again, I've mentioned this a couple times. The defense, maybe, I mean, a lot of these teams are playing each other, so they could both score a lot of points, but one has to win, right? That's another thing. There's any number of things that could kind of go into that, okay? All right, that's tricky. We'll get back. We'll get it. We'll get there, okay? Just keep at it, okay? Next thing, standard deviation of the residuals. Now, you already understand standard deviation. You understand residuals, okay? So it's the same thing, except it's applying standard deviation idea to residuals. What is standard deviation? How far you are away from the average on average. And what's a residual? How far away in the y direction you are, the y value, from what was predicted. So you combine those together, and it's the approximate size of the typical or average prediction error. And what that means is how far on average are the values away from the prediction line, which is the regression line. Now, standard deviation is usually how far away you are from the average on average. The average here is not an average value. The average here is considered the prediction line. Damn it, didn't mean to do that. The prediction line is your average. Like, that is what is expected, basically, okay? How far away these points are from this on average is basically your standard deviation. Okay, So if the points are closer to the line on average, you have a smaller standard deviation of residuals. If the points are further from the line on average, you have a higher standard deviation of residuals, okay? So it's likely to make sense that the further the points are away from the line, your R value is probably smaller, right? Okay, there's more deviation. The residuals, which is always Y direction, is further from the regression line on average, okay? And we'll see that in a second. Whew, lots to do, lots to do. I don't know how long this video is, but I'm tired. Okay, here we go. Okay, here we go. Back in the day, AP Statistics was much more of a plug data into like some statistical analysis software and learn how to do that. Nowadays, you don't really do that as much besides using your calculator here and there. You need to interpret. So this class is much different than what it used to be way before I even taught it, okay? This output is something you would see from one of those statistical analysis softwares. When you go to college, there's some people that have taken this class before that have taken stats in college and tell me about it. They use some of that software. This is the stuff that the actual statisticians use. You don't have to know how to use that software. You just need to be able to interpret what it says. Okay, so notice there are a couple things that the software would not say. It wouldn't be saying y-intercept and slope and explain it. Like those things I added in for instructional effect. But basically what you will see is this right here. And there's a number of things here that you need to know. Next to the word constant will always be a number that is considered your y-intercept. Okay, and that's kind of easy to remember because a y-intercept generally is a constant. It's just a number. It's not affected by a variable. It's just the number that you start at. Okay? The second thing you need to know is they will always give you the explanatory or x variable, and they will give you next to that what's considered the slope, and that is called the slope. And the reason they put the x variable there is because basically you're saying this is the amount of change for 1 unit change of that. So basically you're saying the slope is 0.1629 whatever units are, probably price in this case, per mile driven. Okay? All right. These things over here, don't need to know. Don't need to know. Don't need to know. However, this one you do. S, just talked about it earlier, it's the standard deviation of the residuals. It tells you how far on average the Y value is away from the data, the prediction line. Okay? So on average, the prices are $5,740 away from the prediction line. And then lastly, last thing you need to know, different color, is R squared. R squared is that coefficient of determination. Remember, that is telling you the percent variation. 66.4% of the differences in Y or price is accounted for by the miles driven thing. And this is actually that data that I wanted earlier. Cool, cool. And then technically there's one thing that's not here that you can get, and it's R. And R is going to be the square root of R squared. So if you took square root of 0.664, that would be your R. Now be careful, R squared is always positive. R is not always positive, so what you need to do is you need to look at the slope. Okay, and if I remember correctly, actually I thought the slope was negative for that. Right, the slope should have been negative. So really, this should actually be negative here. Which then separately from that, that would mean that the R is negative, because remember, R is a negative association in this case, negative slope. So if I ever asked you, trick question, what's the R given this output? You'd have to take the square root of this and make sure it's the same sign as that. Okay? So there's a bunch of things here. All of it's stuff you should already know at this point, but it's just using a different mean or mode of inferring data. Okay? So take a second, take a look at this next question, try it. I'll go over the answers here in a second. All right, it's been a second, okay? You read through the thing here. Basically, I can essentially cross this off, cross this off, cross this off, cross this off, okay? You won't need it. Negative 87.12, remember I said next to constant, that's the y-intercept. So the y-intercept here, if a tree had a height of 0 inches, then the expected tree volume would be negative 87.12 cubic inches. Doesn't make a hell of a lot of sense, but that's what it is. 1.543 is always the slope, and this is for the x value technically. So the predicted tree volume increases by 1.5433 cubic inches for each additional increase in height. The S is standard deviation of residuals. So the residual volumes, the residual y values, differ from the regression line on average by 13.40. So how far on average the points are away from the average, which in this case technically is regression line. 35.8 is your r squared, basically saying that the regression line relating height and volume, again, you always say the same exact thing, accounts for 35.8% of the variation in volume. That means the reason that the volume isn't perfectly on the line is only accounted for about 35.8% of that because of this relationship. There's other stuff going on, right? There might be some weather issues, there might be some tree damage, who knows? Okay, I don't know. 35.8% is not a big percentage here. And then what is the R? What's the correlation coefficient? You take the square root, you get 0.598. It is positive because the slope is positive. There you go. Okay. All right, feel free to try this one. Yeah. Okay. Got a lot going on here. We got a computer output, we got the regression equation, well technically it's a regression equation in the output, we have the scatter plot, we have the residual, a lot of stuff going on. What's the equation of least squares? That comes straight from this guy right here. Remember y hat, don't forget y hat. Interpret slope, we did that a million times. That's that guy right there. Increase for every 1 additional centimeter in foot length. Don't forget the units, don't forget the variables. If you don't say it in context, you're going to get it wrong. Correlation, we just talked about this a second ago, or what feels like a second ago, because it was a second ago for me. You take the square root of the r squared, positive, because the slope is positive. Explain the significance in context of S. Remember that standard deviation of residual, so that talks about how far on average the y values, the student heights, differ from the regression line, and it's by about almost 8 centimeters there. Okay, is a linear model appropriate? And yes, look at the residual plots. Okay, now obviously I give you the scatter plot too, so you probably can tell from there it's pretty appropriate, but scatter plot, random scatter, no obvious pattern. And then last thing here, we'll skip the putting it all together later, we'll maybe do that in class, but for right now, we talked earlier the DUFs, right? The direction, unusual patterns or outliers. And the reason we didn't just call it outliers is there's actually a couple things to do here. There's 3 different vocab terms: outlier, high leverage points, and influential points, and they mean something slightly different. An outlier in scatter plots have large residuals. Large residuals means they're very high or very low compared to the prediction line. Okay? An outlier is a point that is very, very high or very, very low compared to the regression line because there's a high residual or a low residual. Okay? Which of these 4 have an outlier? Hopefully you said this one, case 4. Reason that this is considered an outlier is it's really far in the y direction from the equation. Okay? None of the other ones have any points that are really far from the regression line. So technically those aren't called outliers. And you might say, well, what the hell would you call this thing? It's like way far away. This is not the same outlier as you would think in one variable data. Yes, if you did a 1.5 IQR type thing here, that would be wholly outlier. Not here, okay? Outlier, large residual, very straightforward. Points with high leverage points have much larger or smaller x values than the other points. Okay, the reason they're called high leverage points is because they're so far away in the x direction, they have a lot of leverage in terms of like creating the equation. If you took those points away, the data, like the equation would likely drastically change, potentially, okay? So in 2 different cases here, you have a high leverage point that has an x value very far away. This one has an x value that's very far away from the other points. And this one has an x value that's very far away from the other points. Okay. All right. And then lastly, an influential point is any kind of point, which could be technically one of the other ones, any kind of point that if removed substantially changes the slope, the y-intercept, the correlation, basically anything. Okay, so is an outlier an influential point? Yes, because if you took this point out, since the regression data is including that point, when you take that out, that is very different from the pattern of data, so it would very likely change most everything drastically. And there is no value for drastically, just conceptually drastically. So that, you can have an outlier, and it likely is considered an influential point. Can you have a high leverage point that maybe is not an influential point? And the answer is yes. Look at this one right here, okay? It is very far away. That is definitely a high leverage point because it's very far away, x direction. However, based on this pattern, and again, we don't have a perfect story here, okay? Maybe this is hard to tell a little bit, but it seems as though this is, if you just focused on this, it's not a perfect correlation, but that kind of seems to be generally okay. If you continue that pattern, this point is right on that line. Meaning, adding or subtracting this point does not change the slope because it seems like it would have been on the line anyways. It doesn't change the r because it's right on the line, right? It doesn't change any of those things. So even though it is definitely a high leverage point because it's far away, adding or subtracting it, it's really not an influential point because it doesn't change some values significantly. Is it important for the data? Yeah, it's important to understand, but is it going to change anything? No. Whereas this one, not only is a high leverage point because it's far away, it does not follow the pattern. If you looked at this regression data, which had to include that point, this would change drastically if you took this out. If you took this point out and that's not there, it would go back to kind of what we saw in that last graph. That's a huge change. Everything changes there, okay? So that would be considered an influential point. Okay, so that's kind of, I just went through this a little bit. Again, those, it's just vocab, you're gonna need to know those. Be careful not to just call anything an outlier. This is not an outlier in Scatterplots, okay? High leverage point. You can have, outliers are definitely gonna be an influential point. High leverage points don't always be an influential point, okay? Skip this last page here. We'll do this in class at some point. We won't do that right now. I'm gonna cut you off. It's a lot. You're gonna have lots of time to practice, lots of time to get better at this, lots of activities and different